Hi, I'm Judy. I'm from Yale. So I have Protochips Aduro, used to be called Aduro, double tilt, and I recently upgraded it to something, I forget Fusion. Okay, but today, so I'm just going to show you some results that we've been able to get with the Protochips Aduro holder. Okay, so let's see, can this play? Okay, so this is sort of the latest experiments that we did. This is metallic glass, so this is amorphous metal in nanorods so that we can directly image them inside the microscope. And we did this experiment in Brookhaven because Yale, using the aberration-corrected machine in Brookhaven. Yale does not have an aberration-corrected machine. It's about 23 nanometers, so we're going through and imaging atomic plane by plane growth of metallic glass nanorods. And there's a lot that we can learn by doing this type of experiment. So this is heating experiment. Okay, so over the last 5 years at Yale, I think my research theme is really looking at phase transformations of nanomaterials and correlate the phase transformations with their changes in either electrical or electrochemical properties. So that's what I'm interested in. So the approach, the ultimate goal that I want is to do in situ TEM of a nano device where the stimuli is either thermal heating or electrical pulses. Electrical pulses could be another thermal heating or just voltage pulses. Currently, we're covering pretty wide range of materials, but today I'm going to focus on phase change memory. So this is a chalcogenide glass of there's a spelling mistake here. Germanium, Ge, antimony, and tellurium, and metallic glass nanostructures. So metallic glass nanostructures is multi-component metal alloys. So it's got platinum, nickel, copper, and phosphorus. That's the system I'm studying. Quite complex system. So I'll share with you these two results. Okay, so at Yale, we have a pioneer, Jan Schurz, who can make nanoscale metallic glass nanorods. So these are platinum-based metallic glasses, and we can push it down to about 10 nanometers at a pretty large scale. And for individual rods, we can go down to about 5 nanometer in diameter. Aspect ratio ranging from, if it's short, 5 to up. They have a lot of applications commercially because you can, these are amorphous, their mechanical properties are quite distinct from their crystalline counterparts. Even if the chemistry is the same, you don't have any defects, right? So they can be stronger, but yet ductile. Okay, so they can be stronger than steel. Jan Schurz specifically developed nanomolding thermoplastic forming process to make these rods. And because you can choose compositions and don't have to worry about their crystalline structures, there's a good amount of materials properties that you can engineer. For fundamentally understanding nucleation and crystallization, I think this system is also attractive because the crystallization kinetics is pretty slow. So we can watch the events happening even with a regular CCD camera. With a K2 camera that's now in the market that gives you upwards of 1,000 frames per second, several thousand frames per second, you can really catch all the events in metallic glasses because the crystallization kinetics is slow. There's a chemical complexity, so it gives you a chance to test the limits of nucleation theory. The classical nucleation theory is a monatomic system. It doesn't care about the chemical differences. But all the technologically relevant materials and scientifically interesting materials we study are chemically complex systems, right? So the simple question I had when I bought the holder was, let me just study crystallization kinetics of these rods. I'm sure something will change at the nanoscale. So that's how I sort of jumped into this field. The way we make this is you first have a bulk metallic glass film. These are micrometer thick plate. And then you heat it a little bit, but still below their glass transition temperature, and you push it through a mold. So this is aluminum anodic aluminum oxide. So as you push it through, because this is a little bit high temperature, it's kind of viscous, so you can push it through, and then you etch away your mold, okay? And then sonicate off to break these rods, okay? So you collect them. So you can imagine just drop casting these onto a heating holder chip. These are the bulk values for this system. Glass transition temperature is at 230 Celsius. If you go above 285, then you're going to start crystallizing these. Again, these glass state is the metastable state, so ultimately it wants to crystallize. Over 400, it's going to melt. Okay? So these are the bulk values. So here's one particular rod. I'm using a regular TM. This is not aberration-corrected TM. Here's a bright field image of one rod at room temperature. This is in dark field. Okay, I'm just randomly putting my objective aperture somewhere. Uniform contrast, so it's amorphous. Now I heat it above the crystallization temperature, so now it's sitting at 350. So in dark field, it's now clear that it's much easier to pick up crystalline grain because there's an intensity contrast. It's a diffraction contrast. So the bright regions, you know it's crystallized. Now if you're at high temperature and long enough, then it's going to melt and it's going to ball up because of the surface tension. It's liquid. Okay. So then what we did is to ramp these rods at about 2/3 degree per second from room temperature to 900. And repeat that experiment as a function of the nanorod diameter. Okay? So this is all in dark field mode. This is a 50 nanometer rod diameter. Now we're ramping. I've sped up the movie. So you see that it crystallizes at around 255 degrees Celsius. Here is now a rod that's 20 nanometers. Okay. This part is 20 nanometers. Actually, it tapers down, and this necking, this part is actually below 5 nanometers in diameter. Okay. So this 20 nanometer region crystallizes around 294 degrees Celsius. Okay. So it's crystallization temperature. The onset of crystallization temperature is different. Here's a 5 nanometer rod. So we did some post alignment, but obviously we didn't do a good job. So here, it's over 300, it doesn't crystallize. Okay, now 1 grain pops up, but it doesn't really grow, even though we're continuing to ramp up. Okay, so the crystallization temperature is all over the place. This is, again, the onset of crystallization temperature. One thing to note is, especially if you want to do an atomic resolution heating, you want to care about the stability of the holder, because you don't want to be moving, trying to look at where your sample is, rather than, right? You want to be looking. You don't want to be tracking. As a reminder, bulk crystallization temperature is rock solid at 285, right? So something changed at the nanoscale. So we just go ahead and do it as a function of number of different nanorods, okay? Just repeat it. And the onset of crystallization temperature, we try to quantify this by doing the following. We know the regions that do not crystallize because you just watch the movies. So we looked for intensity contrast, or the contrast jump, okay, compared to this region versus some background region. Okay? So when the slope changes, right at the onset of the slope change for the intensity contrast, we call that T sub x, onset of crystallization. Okay? So you see that as we initially decrease the diameter of the rod, the onset of crystallization decreases as well, but then it takes an upturn. Okay? So it has this non-monotonic behavior. Here's a summary as a function of the diameter of the nanorod, crystallization temperature. Here's the bulk value. So before this study, there was a traditional differential scanning calorimetry experiments done on nanorods, where they collect many of 200 nanometer rods, and then you look for when it crystallizes. The challenge here is a signal-to-noise ratio, right? To have a reasonable signal-to-noise ratio for 100 nanometers rod diameter, you need billions of them, right? So if you were to do this for smaller rods, that's a very difficult experiment. With these results, it's reasonable to expect that, okay, the crystallization is easier to happen, and then you would think maybe that's because you have more surface, and heterogeneous nucleation is easier than homogeneous nucleation, because the nucleation barrier is lower. So this trend makes sense, right? So now what we see is that if you go further below, then the trend reverses. So why is that? Various factors, we ruled it out. We think there are 2 factors that contribute to the upturn in crystallization temperature. One is the probability of nucleation, meaning if you think that the nuclei density is fixed, but you reduce the size of the rods, then the absolute number of nuclei that you will have decreases for a small rod, right? So for a very small rod, maybe you don't have any nucleus. Then you have to first nucleate, and that takes a lot of energy. So how do we verify that? So this is an indirect way to verify this. For larger diameter rods, let's say 50 or 120 nanometers, we're going to assume that you will always have some nuclei present. If you always have some nuclei present as we repeat the experiments, the crystallization temperature should be steady because you have nuclei to begin with. If you don't have nuclei, let's say for smaller rods, since nucleation is somewhat of a stochastic process, it's a probabilistic process, there should be a scatter in your crystallization temperature. And that's what we see here. So for smaller rods, we have more scatter. So if you look at the standard deviation of the scatter, the crystallization temperature as a function of diameter, we see that it increases. It's still smaller than the overall trend that we see, which is nice. So we think that the upturn of the crystallization temperature for very small rods is simply that we don't have nuclei in the sample. Okay? So, and that fits with the classical nucleation theories. The second one is from the observation, and that is that the growth rate itself also slows down for small rods. So here is a movie. You're going to see the grain growing, and then it develops a necking here where it's a little bit narrower. And then the grain growth gets suppressed quite a bit. Once it passes, it picks up the speed again. Okay? So in the narrow region, the growth rate slowed down. So here is the just snapshots showing the growth front. And so we were ramping here. The temperature here is somewhat of a time series. And then you can see that right at the necking region, the growth rate is greatly suppressed. This is not just because of the necking. So here, these are all various nanometer diameter. These are all various diameter nanorods. And what we're saying here is that when we look at the growth rate as a function of diameter, the growth rate is also small for smaller rods. Okay? So this is pure observation. Later, near the end of the talk, I want to go back and sort of try to give you reasons why that may be. So if we sort of include the heterogeneous nucleation, which can explain the first decrease in crystallization temperature for larger rods, and also the fact that the growth rate slowed down. So another way to say it is that the viscosity is 1 over diffusivity, is size dependent, then we can recapture what we observe pretty well. Okay. So that was our first work. Okay, so we summarize and wrap that up. So simply put, the fact that you don't have as many nuclei in small samples and somehow the growth rate being slowed down, that controls the nucleation kinetics, right? And it was enabled by just directly looking at crystallization processes inside TEM. No aberration corrected atomic resolution, a lot of dark field systematic studies. One thing that was very important was, again, the stability. Because as you heat, if the thermal expansion of the chip changes quite a bit, right, then you have to there's a lot of drift, right? So you want to worry about that. Now, the fact that the crystallization temperature changes as a function of the nano diameter means that actually there's a processing window that changes with the size. So one of the reasons why bulk metallic glasses is so fantastic is captured in this figure. So this is an opinion piece from Jan Scheurer. This is strength of a material as a function of processing temperatures or the temperatures. Okay, so steel obviously is very strong. We use steel for building buildings, but it's very difficult to process because to mold it or to make it into a structure, you have to heat it really to a high temperature, right? This is energy costly process, and also safety is an issue. And when you heat it, it suddenly becomes like liquid, right? Now, for plastic, plastic is very easy to form. In some moderate temperatures, they're viscous, you can form it whatever you want. That's why we're full of plastics. And they're relatively strong, right? You can carry a bag of apples in a plastic. It's relatively strong and pretty easy to form. Metallic glasses combine both, right? So here is a platinum-based and zirconium-based metallic glasses. At room temperature, stronger than steel. You can form them like the way you form plastics at a moderate temperatures, 2 to 3, 400 degrees Celsius. It's great, okay? The only reason this is expensive right now, but it already serves a very niche applications very well. So the fact that the crystallization kinetics changes means that for a nanoscale structures, you have to know the processing window that you can do this in, okay? And there's now what's called critical heating rates and cooling rates that are coming into play. So this is time temperature transformation diagram. So I will explain this to you for those of you who don't know. I've never seen this before I started studying nucleation. This is liquid here, okay? When you cool the liquid, it's going to crystallize, right? But if you cool the liquid super fast, it's going to become glass. Frozen liquid is glass. It takes some time to crystallize, and at high enough temperature, you don't have a much thermodynamic driving force to crystallize because you have a lot of jumping motions. That's why it takes longer to crystallize here. At lower temperature, now you're too cool, so even though there's a thermodynamic driving force to crystallize, atoms are sluggish. They're slow to move. That's why it also takes longer time to crystallize. So it's got this shape. So heating rate. Okay, so if you heat the glass really fast, it's just going to become liquid, bypass the crystalline part. You can imagine doing this in experiments where I just heat it really fast using, again, the protochips holder. If I don't see any crystallization events, either by diffraction peaks or intensity contrast, maybe I mark it as a circle. If I heat it slowly, then I'm going to see some crystalline events. Right at the nose is the critical heating rates. So maybe sometimes you see a crystalline event, other times maybe you don't see it. So you do it many times right here to sort of mark where your nose is. This is experiments. We actually recycle our rods. So the way we recycle them is that we go to 900 degrees Celsius for less than 5 seconds to melt everything. And then we quench it as fast as we can. And then now we vary the heating rates. Okay? So here's a movie, a 5,000 degree per Celsius rate. So this is actually higher than the critical rate. So the contrast is not so good. But we don't see any diffraction peaks that pop up. When you heat it slowly, so lower than the critical heating rate, then you see the diffraction spots pop up. And it becomes liquid, so it's going to be amorphous again. So here's the summary of the data. So as a function of the nanorod diameter, we are repeating experiments at many different rates. Okay? And right here is the critical range. Okay? So one sanity check is that this result agrees with our previous result because this is a rate, so it's sort of inverse of the crystallization temperature. So this non-monotonic shape, we preserve that. So that's good. This was critical heating. You can do the same thing for the cooling. If you quench the liquid, then it becomes glass. So for silicon oxide, silicate glasses, the quenching rate can be rather slow, right? If you quench it slowly, it's going to become crystalline. And then again, you have a critical range. Okay? So we repeat this, but now here we go to 900 degrees Celsius, and now we vary the cooling rate. Okay? So here's an example. When we cool it faster than the critical rate, at room temperature, you don't see any crystalline grains. If you cool it slower than the critical rate, then now you see the rods have crystallized. So here's the data. Okay, so again, it has this non-monotonic rate size dependence, as we would expect. So what we did is to overlay the critical heating rate and critical cooling rate together as a function of diameter. Okay? So you see that the critical heating rate is about 2 to 3 orders of magnitude higher, 1 to 2 orders of magnitude higher than the critical cooling rate. That's been observed in bulk samples. And the way we explained this in the field was to recognize the fact that the temperature spot where a lot of nucleation events happen is at a lower temperature spot compared to where a lot of growth happens. So if you're heating, you first created a lot of nuclei, and then now they grow. Okay? Now if you're cooling, you're first coming down from this side, so you don't have that many nuclei. Okay? So there's nothing to really grow. And by the time you create nuclei, your growth is slowed down. Okay? So that's a way to explain critical heating rate is faster, meaning it's easier to crystallize coming from glass up. So the rate has to be faster. So that's confirming what's already been observed. What was new to us was the fact that below about 35 nanometers in diameter, the critical heating and cooling rates emerged. Okay, so that was never observed. I mean, people never looked at these small sizes. So we see that the asymmetry at larger scale disappears. This can still be explained by classical nucleation theory, simply for the fact that in small rods, you simply don't have that many nuclei. If you don't have that many nuclei, it doesn't matter where this window happens, because you just don't have that nuclei. Thereby, the kinetics should be similar for both heating and cooling. Okay? Now, the fact that you don't have that many nuclei actually is a way to create metastable, novel crystalline phases. This is a multi-component metallic alloy. If you crystallize this in bulk scale, it's going to form a thermodynamically stable binary phases. Okay? Phase segregation happens. At the nanoscale, because you didn't have any nucleus, when you crystallize, you sort of lock into that single crystalline grain, a single crystalline phase. So here is a nanorod that we observed to be a single crystalline phase, which you would not expect for multi-component metallic alloys. And it's a single grain. And the crystalline composition is equivalent to the glass composition. Okay? So this is very surprising. Of course, for larger rods, they can contain many grains, so you can have a polycrystalline product with also phase separation. So here's a copper-rich region. This is a copper-rich region here, and there's a nickel-rich region over there. Okay? So chemical heterogeneity, which you would expect at the macro scale, doesn't happen in the nanoscale. So then we finished the phase diagram. So here was a critical cooling rate, the shape. And underneath, we know we can crystallize. We've sort of mapped out where the single crystallization can happen and where more expected polycrystalline phases will come out. So for small rods, because you don't have any nuclei, you will have single crystallization event. If you also force the kinetics to be very fast, then you can also have a single crystallization event. Okay. So we sort of coined the term of nucleation starvation, borrowing from the dislocation starvation and how dislocation starvation drastically changes the mechanical properties of nanoscale metallic systems. So here, starving nuclei may be a way to get at metastable new phases. Okay. Okay, so far using just regular TEM, a lot of dark field TEM studies with the protochips at your holder, we've made a number of observations. The crystallization temperature have this upturn due to the lack of nuclei, and that can also explain the merge of the critical heating and cooling rate together. And then the lack of nuclei meant that we can have a new single crystalline phase out of a multi-component metallic alloys. These were all ramping experiments. I was ramping the temperature. So now we looked at doing isothermal experiments, where we directly go to a set temperature and watch the grain growth. Okay? So you can imagine doing it in two different ways, coming down from the liquid side and doing crystallization, or heating from the glass side and doing crystallization. Okay? So the simple, naive classical nucleation theory will tell you that because you're coming from two different sides, maybe the nucleation rates would be different. But if you are at the isothermal temperature for quite some time, the growth rate should be the same. Because growth rate is diffusion, and diffusivity is purely a function of temperature. So this is the same rod. We just recycle our rod. We're doing isothermal growth at 420 degrees Celsius. The first one is coming down from liquid side. The other is from the glass side. Okay. And what we observe is that the growth rate coming from the glass side is much faster. Okay. And this is coming from the liquid side. I don't know if you notice, when we go from 900 to 420 degree directly, there's a jump. Because you're like changing the temperature drastically. I think it has to do with the way chip is designed. So some companies bypass this. So the growth rate is different, okay? So then that's when we went to Brookhaven National Lab to do aberration-corrected experiments. So here is a 23 nanometer rod. We're heating it from a glass state, sitting at 360 degrees Celsius. I'm kind of zooming in into the middle of the rod. This is the amorphous state up top. Now we have the single crystalline grain, and then we're going to watch the grain growth, right? This is using the K2 detector. I think that we ended up using 500 frames per second frame rate. But to get the signal-to-noise ratio that gives you atomic resolution, we averaged 100 frames post-processing. I think we can probably reduce that frame rate, but we felt that we were catching all the events necessary with 100 frame averaging. Okay, so here is now just the time snapshots. So what you see is that even though this is isothermal growth rate is not constant, right? If it's purely diffusion controlled, growth rate should be constant because diffusion is a constant at the same temperature. So the growth rate is not constant. Okay, this is a 1 second time difference. Not only it's not constant, it seems that suddenly it jumps and then it kind of gets stuck and then it jumps again. Okay, so there's a little bit of fluctuations. So here's the growth rate we can measure as a function of time. So we can do this for different size of the rods. These are all isothermal temperature experiments at the same temperature. Again, even though this is isothermal experiments, growth rate are all over the place. Okay, they're not the same. And the blue means I'm doing crystallization from the liquid side. The red is coming from the glass. So another thing you see is that when you're crystallizing it from the glass, your growth rate is much higher. Okay, so right now we're in the middle of analyzing these data, but it certainly shows you that classical nucleation theories fail here. And what we believe, do I have this? Okay. What we believe is that there is substructures in the glass that is enhancing crystallization. Okay, so this is now idea that is quite common, and then I just borrowed this paper from a chalcogenide phase change memory field. We know that in liquid you can have clusters, just small number of atoms, somewhat arranged on a short order basis. You can have lots of clusters in liquid, but they're not thermally stable because they're not meeting the critical nucleus size, right? So there's an energy barrier, energy cost is creating surface, so they would just go back to the liquid phase, right? So these subcritical clusters or subcritical nuclei will fluctuate in and out of your liquid. Generally, you would think that at high temperature, the relaxation time of these are really fast, and that they would not participate in growth because they are just going in and out really quickly. What we believe is happening is that we create these clusters in our glass state, and that they're quite stable. And that these clusters that are rather stable then enhance the growth rate. We did working with the Corey O'Hearn's group at Yale, we did a very simple binary Lennard-Jones molecular dynamic simulations. We've kept the middle portion of the rod crystalline, and then the two ends amorphous, and we watched the growth dynamics. And this is a little bit complicated, but what we did is we varied the quenching rate when we make the glass part here. The idea was that the faster the quenching, the less number of clusters you would have in the glass state. So if the quenching was faster, then the growth rate should be slower because you don't have as many clusters, okay? And that's basically what we saw. So R is the quenching rate. So the faster the quenching rate, the mean growth rate was slower, and also the fluctuations that we saw in the growth rate was also lower. This is, of course, simple binary Jones, but I think it can capture some essence of what we see. Here's a proof of the subcritical nuclei being very stable. Here's about a nanometer or 1.5 nanometer cluster that pops up, and then it's rotating around. And it's quite stable for 6 to 7 seconds, even though we're sitting at 340 degrees Celsius. And then once it disappears, we never saw it again. Okay? So you see that it persists about 6 seconds. Okay? So to sort of see if that's really true, we do an experiment where when we are heating from the glass, instead of going as quickly as possible to our isothermal temperature, we kind of went in some baking time. And the idea was to create some clusters. So this is a little bit difficult image. I think the scale bar here is probably 5 nanometers. Here is a single crystalline grain that we have. This is actually glass, but it's not really glass. It's full of small clusters that are arranged. Okay? And as this grain is growing, they're quite stable. They may rotate, they may disappear, but the time frame is, I'm talking about 2 to 5 seconds. Okay? Certainly long enough to really couple to the growth dynamics. Okay, so so we're ongoing with these studies, and because of the chemical complexity of the metallic glasses, I'm excited about the possibility to test the limits of classical theories now using this system. And sort of see where the classical system fails. I mean, at the atomic scale, classical system fails because it doesn't have any picture of the atomic atoms, right? It's just continuum model, thinking about single element. So I think this is a good system to sort of see where the phenomena and the physics deviate from the classical theories. That was rather fundamental fundamental nucleation and crystallization studies using metallic glasses. Let's move to a bit more application-oriented studies. So this is work in collaboration with IBM Watson Center, which is about an hour and a half away from Yale. So it was like I buy the in situ holder with part as my startup package, and maybe the first week I'm tinkering with it in the TM. The IBM engineer is there to use the TM, and then we talk, and he's like, I really want to do this. I've been wanting to do this forever. So that's how this happened. Of course, I think it had about 2 years of like inactivity, but finally at the end we got this done. Okay. So phase change memory challenge. Memory is limited. The true volatile memory we have very little of. The storage, we can have a lot of storage, cheap, terabytes, no problem. But the computation power is just becoming ever more powerful. We have ever more data-intensive applications that we want to run. So this memory is very meager, right? You can't run your computer programs on this memory. People try to use this as a memory, but it's really slow, right? So we want something in between, and it's called storage class memory. There are some companies, I think it was Intel, that announced that they're going to sell storage class memory. This was probably, the news was already 2 years ago. So the storage class memory is a memory, but has the attributes, the good attributes of storage. Meaning, storage is good because it's non-volatile. The information stays there if you power it off, right? And it's also cheap, so you can have a lot of it. The downside is it's slow. Memory is fast, but they're volatile. You have to have the power on, and it's expensive. So we want fast read and write, non-volatile, so even if the power is off, you can keep the information. And we want it cheap, so we can have a lot of, right? And there are a lot of memory technologies for this flash, MRAM, PCM. And so PCM is one of the technologies that perhaps can realize this storage class memory. The working principle of PCM is that it's a chalcogenide glass, usually some variant of germanium, antimony, and tellurium combined. You can very easily go from amorphous to crystalline state by a little bit of joule heating using usually about nanosecond voltage pulses. In the amorphous state, the resistance is high. In the crystalline state, the resistance is low. So here is your bit. Okay? So it's non-volatile because your information is stored in the crystal structure. So even if the power is off, the crystal structure remains. You can do rather fast switching. Some of the latest papers talk about picosecond switching, time scale. Stability is they don't address stability, but they can do picosecond switching. Down the road, it's easy to conceptually scale this. There's no difficult architectures like in MRAM. It's a very complex architecture, so scalability can be an issue. And we've now seen high endurance. Okay, so when I was at Stanford as a postdoc, which was many years ago, we made some academic version of PCM, right? Just thin film, sputtered film, and show, yeah, we can do this in situ. So when I moved to Yale, now we started working with IBM on their next generation confined PCM cell. So this is the conventional mushroom cell you can buy, right? Here's your GST thin film. You have a bottom electrode that just locally changes the phase of the GST. The new one that IBM made, it's a plug. So they've developed processes to fill this plug very reliably and densely. And the novelty is that it's surrounded by this metallic surfactant layer. The idea of this metallic surfactant layer is that even if you create a void, you still have a path for the current in the presence of a large void, and could perhaps prolong the cycle numbers. And in fact, last year, they showed record number of 2 times 10 to the 12 cycles, which was quite an achievement. And the engineer just stopped the device. The device did not fail, but the engineer just stopped the device. Okay, so the idea is simple. Let's just study these devices inside TM. Okay, preparation can be difficult. So you do a focused ion beam, but at the end of the day, after all this process, you want your device to be functioning, right? So it's not just about getting atomic resolution imaging, but making sure your device is not damaged. So of course, working with the IBM engineers who's just FIP specialists, we learn tricks to do this. And here are some numbers that we use for the reset. It's about 40 nanosecond, pretty high voltage, 3.5. Usually, so the voltages that we use in situ is different from the wafer scale because our devices at the end do not behave like when they're in the wafers. I think we use about 3.5 to 4 volt here. And then for the set one, we have a long trail just to crystallize it. We spent a lot of time to automate this whole process. Okay, you don't want students to be doing the switching because by the 7th one, you're going to make a mistake. There are multiple equipment that you have to operate and at the right sequence. So there's a lot of room for error. Here's now we're switching. This is the resistance values that we're reading. Here's a crystalline region that's coming, showing and disappearing. Okay? So what you notice, actually, it's clear in the beginning, is that not the entire plug does not crystallize. Only a portion of it crystallizes. And usually a bottom part, there's a large part in the bottom that crystallizes, and a little bit in the upper part that crystallizes. Okay. So here, this device, we were able to cycle about 170 cycles up and down. These values are not the same as the wafer values, but here is now our on and off. And we can now do statistics because we have a lot of cycles. So we can say a lot of times it's about 40% crystallization. That's the bottom little part here. And the other times, somewhere in the center is another crystallization fraction. So we have these clusters of crystallizations. This is kind of promising if you think about multi-cell operation, where you want to have 2 different resistance states and use that as 2 different levels. I think the amount of control is not quite fine-tuned yet. The one thing we noticed was that you can form voids if you don't do this carefully. So here, current direction is this way, and then we form a void here. Now, we can reverse the direction of the current, and then we can fill the void. And this is pretty reliable, reproducible process. So this is now we're just reproducing it many times. And when you have a void, you have an empty space, so the resistance is going to be higher. Okay? So the community realized that this happens, obviously, and then they knew that this had to be with some sort of electromigration, right? You have cations and anions. You're producing an electrical field, so these cations will move to anodes, anions will move to cathode. I think what we showed here for the first time is to the degree of the drastic change it can actually happen. So what we found was that a single pulse can move the antimony, which was originally sort of uniformly distributed, all the way to the anode. Antimony is cathode. So single pulse can move the entire antimony down. Okay? So that's how drastic this can be. So when we reverse the current direction, you see the antimony, which was near the bottom, now go up to the top. Okay? So that's the electromigration that forms the void. And the fact that this IBM device has a metal surfactant layer means that initially failed device, where more than half of the device was a void, you can gradually fill it back because you have a very resistive element where the current can still flow. Okay? So you can heal the device. Okay, so it's right about there. Now it failed. So here, the resistance was initially high. You're measuring resistance through the metallic surfactant layer. Once it's filled, then you can do some switching. Okay, so couldn't resist myself from calling it self-healing. So I think maybe a take-home message could be that instead of using the same polarity for the set and reset, maybe use a opposite polarity. So then if the antimony moved up, you try to move it down the next cycle. This is actually a lot of overhead design in the wafer scale. But as an idea, we proved that, yeah, this way of running the device works. Okay, okay, so I just showed you, I guess, how we use the in situ heating holder. So this is an in situ heating electrical holder. One was to do a lot of just heating and then study crystallization dynamics. And the other was to actually run devices. The electrical pulse, we are using nanosecond type pulses. And when we look at the shapes out of oscilloscope, it's pretty good, right? So there are no capacitive or inductive elements that would slow down the or change the pulse shape. So with that, I will conclude. So most of the work that I talked about was in collaboration with the phase change in memory was with IBM, Dr. Yuzu, Wang-Kin Kim, and Bright Sky at Yale, bulk metallic glasses. The sample was from Jan Schurer's group. The molecular dynamic simulation was done in Corey Orhan's group. Some of the aberration-corrected study on metallic glasses was done at BNL with staff scientist Ho Lin Sin. Song Woo-Son is a postdoc working very closely with Terry, a grad student, to do the bulk metallic glass studies, and Terry did the IBM PCM work. So thank you very much.